Alice wants to pay Bob. Thousands of anonymous Bitcoin nodes will verify her transaction, and they have no idea who Alice or Bob actually are. So how does Alice prove she owns her coins without revealing a password? And how does the network guarantee only Bob can spend them later? The answer isn't encryption. It's a 50-year-old piece of math. To understand how Alice pulls this off, we need one idea from the 1970s, public key cryptography. It's built on one-way functions, operations that are easy to compute forward but effectively impossible to reverse. This creates an asymmetry. You generate a key pair, a private key that stays secret and signs, and a public key you share freely so others can verify. The private key produces, the public key checks. One direction is cheap, the other is mathematically out of reach. Here's the critical correction most people get wrong. Bitcoin does not encrypt your transactions. Every transaction is fully published. Amounts, addresses, everything. What Bitcoin uses is a digital signature. Anyone on Earth can verify that signature against Alice's public key, but only Alice, holding her private key, could have produced it. Encryption hides information. Signatures prove authorship. Bitcoin needs the second, not the first. That distinction is why the network can be open and secure at the same time. So what exactly is a private key? It's not derived from a password or a phrase you choose. It's raw randomness, a 256-bit number, meaning 256 binary digits, each a 0 or a 1. Imagine flipping a fair coin 256 times and writing down the results. That string of bits is your private key. The technical word is entropy, genuine unpredictability. Real wallets don't use coin flips. They use cryptographically secure random number generators called CSPRNGs, which pull entropy from hardware noise to guarantee no one can guess your key. So how big is a 256-bit number, really? We're talking about 2 raised to the power of 256 worked out. That's roughly 10 to the 77th, a 1 followed by 77 zeros. To put that in perspective, scientists estimate the number of atoms in the entire observable universe at about 10 to the 80th. That means the size of the key space is within just a few orders of magnitude of every atom that exists. Here's the kicker. If every single atom in the universe ran 1 trillion guesses per second, starting from the Big Bang until today, you still wouldn't make a meaningful dent in the search. This is why brute forcing a Bitcoin private key isn't a computing challenge. It's a physical impossibility. A private key is a random number. To get the public key, we need elliptic curves. Bitcoin uses a specific curve called SECP256K1, defined by the equation y squared equals x cubed plus 7. Over ordinary real numbers, this traces a smooth looping shape. But Bitcoin computes in modulo a very large prime p, meaning all arithmetic wraps around after p. This is called a finite field, a number system with finitely many elements where addition and multiplication still work cleanly. Inside that finite field, the curve no longer looks like a smooth line. It becomes a scatter of discrete points. Those scattered points are the entire playground for Bitcoin's cryptography. On this curve, we define a strange kind of addition. Take 2 points, P1 and P2. Draw a straight line through them, and that line will intersect the curve at exactly 1 more point. Reflect that third point across the x-axis, and the result is P1 plus P2. It's a geometric rule, but it behaves like a real addition. Commutative associative with an identity element. 2 edge cases matter. If you add a point to itself, P plus P, the line becomes the tangent at that point. If 2 points sit on a vertical line, it hits nothing else, and the result is defined as the point at infinity, our 0. With addition defined, we can multiply. Scalar multiplication means adding a point to itself over and over. 2g equals g plus g, 3G equals G plus G plus G. For Bitcoin's key generation, we compute K times G, where G is a fixed generator point baked into the protocol, and K is your private key. Doing this naively would take K additions, impossible for a 256-bit K, but with a trick called double and add, you can compute Kg in roughly 256 doublings. Fast forward, effectively instant on any laptop. Here is the trapdoor. K equals K times G. Going forward, multiplying your private scalar K by the generator G to get the public key K takes milliseconds. Going backward, starting from the public point K and trying to recover the secret scalar K is called the discrete logarithm problem on an elliptic curve. No known algorithm solves it faster than brute force. A trapdoor function means easy one way, impossible the other. And this is what lets Alice publish her public key to the entire world. Anyone can verify it came from some private key. Nobody, not governments, not supercomputers, can figure out which one. Now we have all the pieces. Let's watch Alice actually pay Bob. Alice takes her transaction data and her private key, runs a signing algorithm, and produces a signature, a short pair of numbers unique to that exact transaction. She broadcasts the transaction and the signature. Every node on the network takes Alice's public key, the transaction, and the signature, and runs a verification equation. If the math checks out, the transaction is valid. Alice's private key never leaves her device. Bob receives the funds at his own public key, and only his private key can later unlock them to spend. The same mathematics secures TLS connections on the web, SSH logins, and encrypted messaging. But Bitcoin is the first system where money itself rests on pure math instead of banks or governments. Your keys, your coins, lose them, they're gone forever. Share them, they're stolen instantly. No customer service, no password reset, no appeal. The security guarantee is absolute because the universe itself doesn't contain enough atoms to brute force your key. That's the quiet, radical idea at the heart of Bitcoin. So ownership defined by a number only you know.